When you learn about digital logic, it's useful to make schematic diagrams to help you keep track of key concepts, to know how circuits fit together, to keep track of how a system would be interconnected with another system, those sorts of things. So let's get started with some standards on making schematics. So, first of all, a schematic is really about the intent. There's lots of different standards out there. I want to use some practices in this course that we're going to talk about with this particular video. But I don't want to get too caught up in this has to be exactly this way to the nth degree. And the reason for that is we end up with different scenarios where sometimes the schematic, we really want to have a lot of detail so that we know how to connect different circuit gates together. For example, if you're going to wire up some TTL gates, like we'll do in one of the labs, you would need to know the pin numbers, you would need to know the part numbers, you would need to know which package you're talking about. That particular schematic has a lot of information on it. But sometimes you're just really wanting to know an overall view. It's a different abstraction level, and so you don't have as many details on that kind of schematic. So I don't want to get too caught up in this has to be exactly this one way, but there are some practices that I do want us to start using, and so this video is about covering that. So the first thing is, when you make a schematic, you can make a net list that basically connects things together. And so I see I have this element G1 and I can follow this wire out. It's connected to G3. Here's G1. Again, it's connected over to G2. It's correct, but it looks really messy and it's hard to wrap your head around. And so if you make a different version, and so you press the M key in this graphic, you can do that within the info book. Things are squared up. We have horizontal and vertical wires that make it look just more pleasant to look at. And you can see the same three connectors. And now it's clear what gets connected to what. So we have G1, that has a fan out. That's a word that we will sometimes use. It's one output driving two different gates. Okay, so there's a fan out of 2 in this particular case. There's the corresponding term, fan in. So the gate G1 has 2 inputs fanning into it. All right, so that's some terminology. So notice how much better this one looks that has the orthogonal wires than this one that's kind of a mess. All right, so we'll try to do that as we go through the course. Okay, the next question is, what about when I have to wire something between 2 different networks and there should be a connection or there shouldn't be a connection? So if the wires merely cross and there's not supposed to be a connection, then you don't put a junction dot. Okay, so here would show, oh, these 2 wires are supposed to connect together. All right, but it's a little confusing because now I have 2 things tapping off here. This is a 4-way junction. And when you look at a diagram, it's not as clear as if you stagger things. So if you hit the J button, this shows you 2 clean T-junctions into a connection. And that way it's clear, oh, this is intended to connect to this wire, and this is also intended to connect to this wire. It just makes it a little more obvious. So that's a standard that's used in a lot of different scenarios. Okay. The next thing I want to make it clear, I think it's obvious, but sometimes I need to state the obvious to make sure we're on the same page. Gates work in a direction. You have to have an input side. Okay, so I can press the button A here and you'll see, oh, this is sensitive to the input. And then B, when I press both A and B to be 1, it causes the output to change. So there's a direction to it, input to output, signal flow. That's important with digital circuits. Okay, there are some weird gates that don't have direction or are bidirectional, but we'll get to those later at the end of the course. The other thing that shows up in schematics is an output bubble or an input bubble. Okay, so if you press that key on this infographic, you notice what happens is a bubble appears on the output. So the bubble in digital logic indicates inversion or a negation. Okay, so if I have a bubble on an AND shape distinctive symbol, that's a NAND gate. If I take away that bubble, it's an AND gate. Okay, so you should know about the output bubbles. The other thing about schematics is typically we go from left to right, okay, just like you would read text. You can do the other way. This is technically valid. It's just harder to read when things go backwards from the norm. Now, that being said, sometimes you have a circuit that has feedback. All right, so you have an input direction going forward and the circuit wires feed back. Obviously, when you have feedback, things go back from left to right. So this, again, we're just setting some general guidelines. There will be specific cases where these standards don't necessarily apply. Okay, another thing that is really one of my pet peeves, I really don't like schematic diagrams that have lots of wires showing, okay, because we're just trying to show what connects to what. And let's say I have a clock signal that's routed throughout, this is kind of a ridiculous graphic here, but it's one long wire snaking across the page. It's much more convenient to represent that with a net list with a name, okay? So the implication here is there's not just two stubs coming in here. This is a wire with a signal named clock, all right? And so this clock gets distributed across the circuit. So we don't need to show a wire, even though we know that physically there needs to be a connection, a wire of some form that connects all the parts together. Also, sometimes you have a signal that goes off the page or off the screen or whatever. And so sometimes they'll put a little arrowhead with a clock signal in here, here's a signal that comes from a different place, and you can use that in your schematic. Okay, I also want to mention that standards with schematics have evolved over time. There was a time when IEEE encouraged engineers to start using a shape distinctive, not a shape distinctive symbol for an AND gate and an OR gate. So you just made a rectangle with an ampersand for an AND signal, all right? And the purpose of that, I think, was we were trying to go to printed schematics, and it was hard to typeset shape distinctive symbols. And so there was a push to start converting to just use everything as a rectangle and label it. Okay, you can see where that would help with typesetting and making graphics. But to me, it never really caught on. And most of the time, what you see are shape distinctive symbols. Like here's the shape for an AND gate. We've already covered shapes for OR gates and exclusive ORs and those kind of things. Okay, so standards evolve over time. There was a time when we also were very interested in schematic capture. So we would draw schematics and then from there try to come up with how you would capture that design. These systems evolved into HDL, hardware description languages. And so there's this legacy of that. And yet, because we have HDL, a lot of the documentation of how designs work get caught or captured within the content of the HDL files, because these are describing how everything connects together. So in some ways, that de-emphasizes the use and importance of schematics, because we have just evolved things over time to where a lot of the structure and content of the circuits is described in the HDL. Okay, let's see. The other thing, I think that's about it. This is the part that I wanted to cover. I want you to start thinking about schematics. We'll be practicing using these as we go through the course.